A falling body does not keep the same speed. At first it is slow, then it becomes faster. Galileo found that falling distance follows a square law. Near Earth, we write it as s of t equals 4.9 t squared. The deeper question is, what is the velocity at one exact instant, such as t equals 2 seconds? This is the intuitive idea of derivatives. The formula s of t equals 4.9 t squared gives distance. At t equals 2, the distance is 19.6 meters. But distance is not velocity. To find velocity exactly at t equals 2, we shrink average velocity intervals closer and closer to that instant. From t equals 0 to t equals 2, the average velocity is 19.6 divided by 2, which is 9.8 meters per second. This is correct, but it is average over 2 seconds. It is not the speed at the exact moment t equals 2. Do not think of instantaneous velocity as a completely different idea. It begins with average velocity. A large time interval gives a broad average. A smaller interval gives a more local average. A tiny interval gives an even more local average. The instantaneous velocity is the value these local averages approach as the time gap shrinks towards 0. Think of it like zooming into the graph near t equals 2. From far away, we see a whole interval. When we zoom closer, the interval becomes smaller. When we zoom very close, the curve near the point looks almost like a straight line. The slope we are approaching is the tangent slope. Approach 2 seconds from the left. From 1 to 2, the average velocity is 14.7. From 1.5 to 2, it is 17.15. From 1.9 to 2, it is 19.11. From 1.99 to 2, it is 19.5551. The values move toward 19.6. Approach 2 seconds from the right. From 2 to 3, the average velocity is 24.5. From 2 to 2.5, it is 22.05. From 2 to 2.1, it is 20.09. From 2 to 2.01, it is 19.649. These values also move toward 19.6. The left side averages approached 19.6. The right side averages also approached 19.6. That common approaching value is the instantaneous velocity at t equals 2 seconds. Instant change is found by shrinking an average change interval toward 1 point. On the graph of s equals 4.9 t squared, every average velocity is a secant slope. The curve is the distance function. A secant line connects 2 points. Its slope represents average velocity over that interval. Even a very tiny time interval still gives an average velocity. The derivative is not simply one tiny average. The derivative is the limiting value approached by those averages as the time interval approaches 0. This is why instantaneous velocity is connected to average velocity, but is more precise. Keep the point t equals 2 fixed. A point coming from the left gives left secants. A point coming from the right gives right secants. Both approach the same tangent line. The tangent slope is the instantaneous velocity. This is what derivative means intuitively. For a distance function, the derivative gives velocity. On a graph, the derivative gives tangent slope. It is not the distance or the height. It is the rate at which the distance is changing. The most important correction is this. Derivative is not a strange new object disconnected from average velocity. It grows out of average velocity. But it is also not just an ordinary small average. It is the limit of average rates as the interval shrinks toward 1 point. Average velocity uses 2 times. Instantaneous velocity asks for 1 exact time. To reach that 1 exact time, a second point moves closer and closer. Secant lines approach a tangent line. The tangent slope gives the derivative.